So the next big discussion that we're going to have with respect to Newton's second law is we're going to start talking about two-body systems. Now I'm just going to introduce this with a literal two-body problem. We'll make it nice and simple. But where this is eventually going to go is we're going to start to look at this more from the context of pulleys. We're going to look at the Atwood's pulley and the Fletcher's trolley. Those are a bit more challenging, so we're going to save those for separate videos. But in this case here, we're just going to look at a nice little situation where we have two objects that are connected by a light rope. So using the assumptions that we talked about earlier that I said you didn't have to know, you still don't have to. There's a way that we can simplify these type of problems. So we're going to have, first of all, if we have two objects connected by a light rope, we've always assumed that the tension is going to be the same throughout that rope. And this means that the same force is going to be applied to both objects. The important thing is that they're going to accelerate at the same rate. Because these two objects are going to accelerate at the same rate, this is going to allow us to make a little bit of a simplification. And I will show you that in this example. So we have two blocks. They're made of identical material. One of them has a mass of 10 kilograms. The other has a mass of 12 kilograms. They're connected by a light rope on a level, flat surface. We have an applied force of 75 newtons right, causes the blocks to accelerate. So while the blocks are in motion, the magnitude of the force of friction is 49.2 newtons. So we want to determine the acceleration of the blocks. So this is kind of what we have going on here. So we have a 10 kilogram block, we have a 12 kilogram block, and we have an applied force, or they're being pulled, they're connected by a light rope, and we are applying a force of 75 newtons to the right. And we also have a force of friction. But it's not saying the force of friction on a particular block is 49.2 newtons. It's saying that the force of friction for the entire system, so both of those blocks together, is 49.2 newtons. This presents a little bit of a challenge because we're lacking a little bit of information to handle this question properly. But since these are connected by a rope and the tension's the same throughout the rope, or we're assuming that, this allows us to make a nice simplification for this two-body system. This problem is the same as the following. Instead of having two separate blocks, we're now going to have one mega block that has a mass of 22 kilograms. So this problem is equivalent to this. What we've done is we've simplified it. Instead of having two separate objects pulled by a rope, we're going to assume that they can be treated like one big object. And with the assumptions we make in high school physics, that is perfectly fine. So with that, this is our lovely block. We can draw our free body diagram for this. So this thing is certainly going to have a normal force going up. It's going to have a force of gravity acting down. Now we're told there's an applied force to the right, and we certainly have a force of friction that's going to oppose that, and I'm going to call right positive. Now for this, what we are interested in is the acceleration of the blocks. In the vertical direction, Fn is going to balance Fg just because there is no motion in the vertical direction. So those forces should balance. When we're looking at the net force, we're going to concentrate on the net force in the direction of motion, or we're going to concentrate in this horizontal plane. So we're just going to examine F net in the direction of motion. And it's okay to look at the X and Y motion separately. We've already done that with projectile motion in the previous unit. So for this, I can write my net force statement. I know that the net force acting on this block, and if we want to be explicit that we're talking about the X direction, I could put a little X here. I don't have to. It's going to be this applied force plus this force due to friction. And I know my definition of the net force is ma. We could put that applied force plus that force of friction. And since I want the acceleration, this is what I'm looking for. We're going to divide both sides by mass. So the mass is going to cancel here. We'll get that the acceleration is this applied force plus this force of friction divided by the mass. So the only thing that we have to be really careful with, once again, it all comes down to signs. So my acceleration, we're told the applied force is 75 newtons right. We've called right positive, so we're going to put that in as 75 newtons. And then we're going to add to that the force of friction, but friction always opposes our motion. Friction's going to the left in this case, which is going to be a negative. So where we have this 49.2 newtons, that has to go in as a negative, since it's counteracting the motion. And then we're going to divide this by the total mass of the system. So I should probably also emphasize this as the total mass. So we got this 75, we're adding to this negative 49.2. We're going to divide by 22. So we're going to get about 1.2 meters per second squared. So the last thing is we have to make sure that our acceleration has a direction. Well, this came out as a positive number, so we know right's positive. So all we have to say is that the acceleration is 1.2 meters per second squared and to the right. So with this, what this is telling us is that both of those blocks, each block accelerates at 1.2 meters per second squared to the right. What we've done to simplify this is we've treated those blocks as one big block, but individually they're both going to accelerate at 1.2 meters per second squared to the right, based on the assumptions with ropes and tensions that I said you don't actually have to know the finer points of.